Hello everyone. My name is Sid Sundaresan and I will be giving an update on the progress made by GeneSiC Semiconductor under this BP5 Power America program. Um, uh, so this program started in July 2019 and this presentation is being recorded as of July 27th. And the main task title for this project is to develop 3.3 kV silicon carbide power MOSFETs and diodes. Here's a brief description of the project. GeneSiC Semiconductor plans to qualify and commercialize multiple product lines of medium voltage silicon carbide MOSFETs and diodes. Commercializing 3.3 kV silicon carbide power MOSFETs and diodes is essential for the next generation of electric traction and extreme fast charger infrastructure. This in turn will save energy and create US manufacturing jobs by accelerating the development and large-scale adoption of wide bandgap semiconductor technology made with silicon carbide. GeneSiC intends to produce 3.3 kV silicon carbide MOSFETs and diode chips at the 150 millimeter automotive qualified foundry X-Fab. The main purpose in doing so is to lower the costs, standardize the supply chain, and increase the quality level of production. GeneSiC intends to offer 3.3 kV MOSFET and diode chips to module makers and other interested end users. In addition, GeneSiC is also discussing module manufacturers to prototype 3.3 kV power modules, for example, open source and future industry standard LINPACK and as well as XHV style modules. 3.3 kV silicon carbide power modules offer 100 to 500 times faster switching speeds as compared to state-of-the-art silicon IGBT based modules, up to 150-degree operating temperatures offered by GeneSiC silicon carbide MOSFETs is a significant advantage that can be exploited in many applications. GeneSiC is targeting markets that need 3.3 kV devices in this program. Primarily, this market consists of traction drives, grid-tied charging, and rail auxiliary drives. The use of 150 millimeter silicon carbide foundry model will be a significant disruptor to the 3.3 kV silicon carbide device market. This market is presently in its infancy because it's primarily implemented on 4-inch wafers. The recent availability of 6-inch wafers with thick epitaxial layers has opened up the possibility of achieving low-cost 3.3 kV MOSFETs and diodes using the foundry model. The next part of the presentation, I will describe some of the key accomplishments and results that we have achieved thus far in this BP5 program. On slide number 5, some of the salient results from 3.3 kV 80 milliohm silicon carbide MOSFETs are shown. The breakdown voltage is greater than 3700 volts on resistance less than 14 milliohms centimeter square, threshold voltage greater than 3 volts, and reverse leakage currents less than 1 microamp were measured on these devices. Shown in this slide are the output characteristics measured at 20 volts and the breakdown characteristics measured on 3 different wafers from this lot. As you can see, the breakdown voltage is in excess of 3.3 kV were measured on these devices. We also fabricated silicon carbide MOSFETs with integrated diodes on 150 millimeter wafers, and the results shown in this slide pertain to those devices with 80 milliohm target rating. So on the left, you can see the breakdown IV characteristics measured on these devices, and on the right is actually the third quadrant IV characteristics measured on discrete MOSFETs, which are shown in brown, and the diode integrated MOSFETs, which are shown in blue. As expected, with the integration of the silicon carbide Schottky diode, the turn-on voltage is reduced from about 3 volts to about 0.8 volts. And by integrating the Schottky diode during third quadrant operation, one can notice that at least up to 20 amps, the current primarily flows through the Schottky diode, thereby bypassing the conduction through the built-in PN diode of the MOSFET. We have examined the reliability and robustness of 3.3 kV silicon carbide MOSFETs fabricated in this program. This slide shows the results achieved by performing both short circuit and unclamped inductive switching measurements on these devices. The left graph shows the short circuit measurements, the result of the short circuit measurements, specifically the drain current transients. These measurements were performed at a DC link of 1500 volts with a plus 20 volts and minus 5 volt gate drive scheme. The pulse width is incrementally increased until failure occurs, which was obtained for a 6 microsecond pulse at under these conditions. The right graph shows the unclamped inductive switching transients, namely the drain voltage and the drain current transient. A single pulse avalanche energy of 4.7 joules was obtained from these measurements, which equates to about 11 joules per centimeter squared at a peak drain current of 45 amps. An avalanche withstand time of 50 microseconds was achieved. Next, I will show we show the results obtained from 3.3 kV 1 ohm silicon carbide MOSFETs. Breakdown voltages of greater than 3700 volts on resistance of less than 14 milliohm centimeter squared and a threshold voltage of 3.5 volts and reverse leakage currents of less than 1 microamp were measured on these devices. We also have fabricated 350 milliohm rated silicon carbide MOSFETs on 100 millimeter wafers in this program. Shown in this graph is an example breakdown IV characteristics measured on one of these devices at a VGS of 0 volts. In summary, on resistance of 250 milliohm, threshold voltage of greater than 2 volts and a breakdown voltage of about 4100 volts were measured on these devices. We also fabricated a lot of 350 milliohm silicon carbide MOSFETs with integrated Schottky diodes. The breakdown IV characteristics as well as the third quadrant performance of these devices is shown here. We have looked at the robustness characteristics of silicon carbide MOSFETs with integrated Schottky diodes. These devices show an avalanche energy of about 2.7 joules and a short circuit withstand time of 4.5 microseconds at a DC length of 1200 volts. Finally, we've also manufactured 80 milliohm silicon carbide MOSFETs with integrated diodes, and the results from these devices are summarized in this slide. Finally, some short circuit measurements were also performed by a subcontractor at Ohio State University. We delivered to them two types of devices with longer channel lengths and shorter channel lengths, and they performed the short circuit measurement on both types of devices. So the short channel MOSFET failed after the 5 microsecond pulse, whereas the long channel MOSFET failed after the 7 microsecond pulse. They also compared the average short circuit times for 1.2 kV as well as 3.3 kV silicon carbide MOSFETs manufactured by GeneSiC. Results are summarized here. With that is all the data that I had to show today. Thank you all very much for your attention. Again, special thanks for Power America for providing the funding of this work. And again, thank you and have a nice day.